One part of Earth is at higher risk of impact by an interstellar object. The vastness of space holds secrets, and one of them is the potential threat of interstellar objects, ISOs, to our planet. While we've only encountered a handful of these celestial visitors, the possibility of an impact is a serious concern. A recent study delves into this very question, shedding light on the regions of Earth most vulnerable to ISO strikes. The interstellar visitors. We've had a front-row seat to 3 interstellar objects, Oumuamua, Borisov, and now 3 I/Atlas. These visitors offer a glimpse into the rare encounters between our solar system and distant stars. A historical perspective. Over billions of years, countless ISOs have likely traversed our solar system. Some, perhaps even more ancient than the ones we've witnessed, may have collided with Earth, leaving behind impact craters like the Vredefort structure. A changing solar system. Our solar system has evolved from a chaotic, collision-prone environment to a calmer state. This transformation occurred as rocks accumulated into the terrestrial planets, reducing the frequency of impacts. However, ISOs remain unpredictable, and their influx into our solar system hasn't diminished. Quantifying the risk. The study, titled The Distribution of Earth-Impacting Interstellar Objects, aims to understand the risk. Led author Daryl Seligman, an assistant professor at Michigan State University, and his team delve into the expected orbital elements, radiance, and velocities of Earth-impacting ISOs. Focus on M-stars. The research centers on M-stars, also known as red dwarfs, the most common stars in the Milky Way. The study suggests that most ISOs likely originate from M-dwarf solar systems, based on their abundance. Simulations and insights. The team employed simulations to explore the problem. They created a synthetic population of approximately 10 to the power of 10 interstellar objects with M-star kinematics, resulting in around 10 to the power of 4 Earth impactors. Directional bias. Surprisingly, the simulations reveal a bias in ISO origins. ISOs are twice as likely to come from 2 specific directions, the solar apex and the galactic plane. Solar apex, the direction the Sun travels relative to its neighborhood, akin to driving in a car and encountering more raindrops. This directionality increases the likelihood of ISO encounters. Galactic plane, the flat disk region of the Milky Way, where most stars reside. ISOs approaching from this region have a higher collisional cross-section. Velocity and impact. The study also highlights the velocity of ISOs. Counterintuitively, the ones that could impact Earth have slower velocities. This phenomenon is attributed to the low eccentricity hyperbolic nature of these objects, making them more susceptible to the Sun's gravitational pull and shifting them into Earth-crossing trajectories. Seasonal influences. Seasonal variations also play a role. The highest impact velocity ISOs are more likely to arrive in spring, as Earth moves toward the solar apex. Conversely, winter brings more frequent potential impactors due to Earth's position toward the solar antapex. Risk zones. The study identifies low latitudes near the equator as the most vulnerable regions to ISO impacts. Additionally, there's a slightly elevated risk in the northern hemisphere, where the majority of the human population resides. Limitations and future directions. It's crucial to understand that this research focuses solely on ISOs ejected from M-dwarf systems. The authors emphasize that different assumed kinematics could alter the distributions presented in the study. Impact on observations. Despite the limitations, the findings contribute to future observations with the Vera Rubin Observatory and its legacy survey of space and time. Astronomers will utilize this information to predict the distribution of ISOs detectable by the VRO, paving the way for further exploration and understanding.